This is a video for the solution for the mid-module 5 review sheets. I'm going to be solving each problem one at a time and explaining what each problem is asking you to do as we go. So let's go ahead and jump in and start with problem number 1. Problem number 1 says to let each small square represent 1/6. So they're talking about these squares right here. And using the same unit, and so in this case our unit is sixths, we're going to draw and shade the following fractions, and we're also going to represent each as a sum of unit fractions. So we're going to be creating addition sentences, that's what this sum tells us, with unit fractions, which in this case is 1/6 because we have 1 as the numerator. So for 1 whole, I can just draw a little area model here, and I am going to shade in 1 whole, or each of the 6 equal parts. And to represent that as a sum of unit fractions, I'm going to write my addition sentence. So 1 equals 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. So 1/6 6 times. And so that is a sum of the unit fractions. These are all unit fractions. For part 2 here, we're going to do the same but with 3/6. So I'm going to draw an area model again. And I'm going to shade in 3 of the 6 equal parts. And now I'm going to write my number sentence to show that 3/6 is equal to 1/6 plus 1/6 plus 1/6. And then for part 3 here, which is part 3, we have 8/6. So in this case, we're actually going to need to draw 2 area models because we have a fraction that's greater than 1. And I'm going to shade in 8/6. So here I go. 1, 2, 3, 4, 5, 6, and 7 and 8. And so to represent this as the sum of unit fractions, I'm going to write 8/6, and that equals 1/6 plus 1/6 8 times. So there's 6, 7, and 8. So there we have it for question 1A. 1, 2, 3, 4, 5, 6, 7, 8. Yep, there's 8/6 right there. So for question B, it says record the decompositions. So the decompositions are right up here where we broke them down into the unit fractions. For part 1 and 2 part 1 and 3 using only 2 add-ins. So remember that add-ins are parts of the addition sentence. So like in this case right here with 3/6, we had 1, 2, 3 add-ins. So we need to do that with only 2. So for part 1, we had 1 whole. So in this case, we could say 1 whole equals 2/6 plus 4/6. So there's 1 and 2 add-ins. Or we can say 1 whole equals 3/6 plus 3/6. There's 2 add-ins there. Or we can say 1 whole equals 1/6 plus 5/6. All of these are ways we can show the decomposition of 1 whole with only 2 add-ins. Then we can do the same thing with 8/6. I'm only going to show a couple possible answers. So we could say 4/6 plus 4/6. That's 2 add-ins. Or another one, we could say 8/6 equals 1/6 plus 7/6. And that's going to be 2 add-ins as well. So a bunch of different options. So we only needed to actually show one for this problem here. So moving on to C, we're going to rewrite the equations from part A. So that's all these unit fraction equations up here. But we're going to represent them as multiplication of a whole number by a unit fraction. So for 1 whole, this looks like 6 times 1/6, because we have 6 copies of 1/6. For 3/6, this looks like 3 times 1/6, because we have 3 copies of 1/6. And then for 8/6, this looks like 8 times 1/6, because we have 8 copies of 1/6. So moving on to question 2. Question 2 asks us to cross out the fraction that is not equivalent to the other 3 and then show how you know. So I would say the best strategy for solving this problem and finding the fraction that's not equivalent is to rewrite or find the equivalent fractions for each of these fractions in the largest units possible. So what I'm going to be doing, first I'm going to take 6/4 and I'm going to be thinking about what is the highest common factor between 6 and 4. And I can divide both of these numbers by 2, and so I'm going to go ahead and do that. And that's going to give me 3/2. And I can't divide that 3/2 by, or 3 and 2 by any number, so I know that that's in the largest unit. Halves are my largest unit. Then I'm going to do the same thing with 60 and 40. And I know that 60 and 40, I can divide both of them by 20. And if I do that, I'm going to get 3/2 as well. So since these two are equivalent to each other, since they both equal 6/2, I know that 6/4 and 60/40 are the same. So then I'm going to do the same thing with 12/8. So I can divide both of these by 2, but I can also divide both of these by 4. And if I do that, I'm going to get 3/2, which is the same, which leaves 10/5, of course, as the odd one out. So I cross that one out. And just to prove that that's not equal, if I were to divide 10/5 by the largest common factor, which is 5, I would get 2/1, which is equal to 2 wholes, which is not the same as 3/2. So that was problem number 2. For problem 3, it says fill in the blanks to make each number sentence true and to draw a number line, tape diagram, or area model to represent the problem. So I'm going to first start with problem A. I'm going to draw a area model, and then B, I'm going to represent the problem with a tape diagram so you can see both strategies. So 6/8 plus something is equal to 1. And so in this case, 6/8 plus 2/8 is equal to 1. And so if I were to represent that with a tape diagram here, I would draw my rectangle, which equals 1 whole. I would partition the tape diagram into 8 equal parts. And then I would show the 6/8 by shading in, I've got to fill in this little gap here. Show the 6/8 by shading in 1, 2, 3, 4, 5, 6. And then the 2/8 by shading in 1, 2. And you can see that that fills up the whole tape diagram, which of course is equal to 1. So I have 6/8, which is this right here. And then I have the 2/8, and then the whole tape diagram is equal to 1 whole. For problem B, I have 3/5 plus 1/5 plus 2/5. So I'm working with fifths, so my units will stay the same. And then for my answer, I have 3 plus 1 plus 2, which equals 6. So to show this on a number line, I start with 0. And this is actually, since 6/5 is greater than 1 whole, I'm going to put 1 whole right here. And I'm going to partition this into fifths. And so I'm going to start at 3/5, which is right here. I'm going to make a jump of 1/5 to show the addition of 1/5. And then I end up at 4/5. Then I'm going to make another jump of 2/5 to show the addition of 2/5. And that leaves me at 6/5, which is the same thing as 1 and 1/5. So moving on to the back side of the paper. For problem 4, we have 2 parts here. The first part asks us to use using the fractional unit shown, identify the fraction of the rectangle that is shaded, and then to continue this pattern by drawing the next area model in the sequence and identifying the fraction shaded. So we can see in this first problem here that we have 5 equal parts and one of them shaded, so we have 1/5. And then the second part here, we have 2 parts shaded out of the 10. And then in a third, we have 3 parts shaded out of 15. So what we're doing is we're actually making equivalent fractions. And the numerator, if you notice the pattern, is increasing by 1. So we go from 1 to 2 to 3. And this is happening because we're splitting this 1/5 horizontally by 1 extra section each time. So we have no horizontal split on this tape diagram, or sorry, area model. And then we cut it in half here and then into 3 equal parts here. So our area model for the next fraction is going to be split into fifths horizontally, or sorry, vertically. And then we're going to cut it into 4 equal parts horizontally. And so then we're going to shade in just the parts that are equal to the furthest fifth. So this row right here. And what we've essentially done here is we've created the fraction. Well, we have 4 equal parts that are shaded in, and in total there are 20 equal parts. So we've created the equivalent fraction to 1/5 of 4/20. Then in part B, it says to use multiplication to explain why the first two fractions are equivalent. So that's these two fractions right here, 1/5 and 2/10. So we're explaining why 1/5 is equal to 2/10. And we show this by multiplying the numerator and the denominator by the same thing. So if we multiply 1 times 2 and 5 times 2, we get 2/10. And because we multiplied them by the same number, 2, and we got this as our fraction, we know that these two fractions are indeed equivalent. Moving on to question 5. It says fill in the circle with less than, equal to, or greater than to make a true number sentence, and to justify each response by drawing a model, such as an area model or number line, creating common denominators or numerators, or explaining a comparison to a benchmark fraction. So we're getting an answer, and then we have lots of different opportunities to explain why we got the answer that we got. So starting with the first fraction here, we have 2/4 and 6/12. If I look at 2/4, I can rewrite. I'm going to be using the strategy of creating a common denominator, and I'm going to rewrite 2/4 in terms of 12. So I'm going to rename 2/4 into 12ths. So I'm going to multiply the numerator and the denominator by 3, and I'm going to get 6/12. Since 2/4 is equal to 6/12 and the other fraction is 6/12, I know that these two fractions are equal. Now I'm going to be using a similar strategy for the next problem, except for this time I'm going to create common numerators. I see if I take this initial fraction, not 3/3, take 3/2, and I multiply the numerator by 2, I'm going to have the same numerator as I do as the other fraction. So 3 times 2 and 2 times 2. And so that's going to create the fraction of 6/4. So 3/2 is the same thing as 6/4. And since fourths as a unit are larger than tenths, I know that 6/4 is greater than 6/10, and therefore 3/2 is greater than 6/10. One other thing you might have noticed is that 3/2 is an improper fraction, meaning that it's greater than 1. And 6/10 is not an improper fraction, meaning that it's less than 1. So you could have also determined that since 3/2 is greater than 1 and 6/10 is less than 1, 3/2 is also greater than 6/10. So another way to prove that by comparing it to a benchmark fraction of 1/2. Moving on to problem 6. Problem 6 says that 3 friends brought some juice to drink at the park. Alex, Jacob, and Frank each had identical containers of juice. Alex drank 3/8 of his container, Jacob drank 6/8 of his container, and Frank drank 7/8 of his container. How many containers of juice did they drink? So this problem is asking us to combine all the separate fractions of containers that each of the kids drank. So we're going to be adding all of the different fractions. So Alex was 3/8, Jacob was 6/8, and Frank was 7/8. And so I'm just going to write an addition sentence for each of these fractions. And since I'm working with eighths, I know my unit is going to stay the same as eighths. And now I'm just going to add 3 and 6 and 7 together. So 3 plus 6 is 9, plus 7 is 16. And so if I have 16 eighths, I can decompose this into 8 eighths and 8 eighths. And since 8 eighths and 8 eighths are both equal to 1, I know that what I'm dealing with here is actually 2 full containers. So to answer the question, how many containers of juice did they drink? They drank 2 full containers, which is the same as 16 eighths containers. So there you have it, the solution to the mid-module 5 review that I sent home. So you should be feeling pretty confident and prepared for the mid-module assessment tomorrow. Thanks for watching.